Close your eyes for a moment. Imagine you're floating in space. Stars surround you in every direction, sharp and steady, millions of points of light against perfect blackness. Now, imagine that directly ahead of you, one patch of sky starts to change. The stars behind it begin to slide. They stretch. They bend. They curve around something you can't see. There's nothing there. No object, no glow, no shape. Just a region of space where the stars don't behave anymore. Where light itself is being dragged off course by something invisible. And then, you notice it. At the center of this distortion, there's a circle of absolute blackness, darker than the space around it, darker than anything you've ever seen. A void so complete that your brain struggles to process it. You are looking at a black hole, not a Hollywood version, not a diagram from a textbook, the real thing, and you're falling toward it. If you've ever wondered what you would actually see, actually experience, falling into a black hole, today, we're going to show you. Not the simplified version. The full, terrifying, mind-bending journey from approach to annihilation, based on NASA's latest simulations and the most recent discoveries in astrophysics. If you're the kind of person who looks at the night sky and wants to know what's really hiding in the dark, you're in the right place. This is final. Frontier Space. Hit that subscribe button right now. Tap the bell so you never miss a deep dive. And drop a like on this video. It genuinely helps us reach more people who love the cosmos as much as you do. All right, let's fall into the void. Chapter 1. The Invisible Monster. Before we begin the descent, you need to understand what a black hole actually is. Because most people get it wrong. A black hole is not a hole. It's not empty space. It's not a tunnel to another dimension. A black hole is the corpse of a star so massive that when it died, its own gravity crushed it down to a point of infinite density. When a star at least 25 times the mass of our sun runs out of fuel, it can no longer support itself against its own gravity. The core collapses in milliseconds. The outer layers explode outward in a supernova, but the core keeps collapsing. Past the point of a neutron star. Past every known state of matter. Until all that mass is compressed into a region of space so small it has zero volume. That point is called the singularity. And the region of space around it, where gravity is so extreme that nothing, not matter, not radiation, not even light itself, can escape. That boundary is called the event horizon. Here's what makes black holes so strange. You can't see them. By definition, nothing escapes, which means no light bounces off them, which means they are invisible. You can only see a black hole by what it does to the things around it. And what it does to the things around it is extraordinary. Let me give you some scale. Sagittarius A star, the supermassive black hole at the center of our Milky Way galaxy, has 4.3 million times the mass of our Sun. 4 million suns crushed into a region smaller than the orbit of Mercury. In 2022, the Event Horizon Telescope captured the first image of its shadow. It's out there right now, 26,000 light-years from where you're sitting. But Sagittarius A star is small, compared to what's out there. TON 618, a quasar located 10.8 billion light-years from Earth. At its center sits a black hole with 66 billion times the mass of our Sun. Its event horizon alone is larger than our entire solar system. If you placed it where our Sun is, its event horizon would swallow the orbits of every planet, past Neptune, past Pluto, and keep going. And in January 2025, LIGO detected the loudest gravitational wave ever recorded. a signal called GW250-0114. Two black holes spiraling into each other, merging into one. The collision was so violent that it sent ripples through the fabric of space-time itself. Ripples so powerful that they physically stretched and compressed the 4-kilometer laser beams in the LIGO detectors. 3 to 4 times louder than any gravitational wave ever detected before. The analysis confirmed Einstein's predictions with terrifying precision. General relativity matched the signal to within a few percent. After a century, Einstein is still right. These are not theoretical objects. They're out there. We've heard them collide. We've photographed their shadows. And the one at the center of our own galaxy is waiting. So what would you actually see if you fell into one? Chapter 2. The Approach. In 2024, NASA astrophysicist Jeremy Schnittman created the most detailed simulation ever made of what falling into a supermassive black hole would look like. Using a supercomputer at Goddard Space Flight Center, he traced the paths of millions of light rays as they curved and bent around a black hole with the same mass as Sagittarius A star. Here's what his simulation revealed. As you approach, the first thing you notice is the distortion. Stars behind the black hole don't disappear. They move. The black hole's gravity bends light around itself like a cosmic lens. Stars that should be hidden behind the black hole are instead visible around its edges, their light bent on curved paths through warped space-time. This is called gravitational lensing, and as you get closer, the effect becomes extreme. The entire background sky warps into a ring around the black hole. Stars streak into arcs. Constellations you've known your whole life twist into shapes you can't recognize. The universe behind the black hole is compressed, stretched, and duplicated into a hall of mirrors made of bent light. Then you see the accretion disk. Surrounding the black hole is a flat, swirling disk of superheated gas and dust, material that's being pulled in but hasn't crossed the event horizon yet. This gas orbits at nearly the speed of light. Friction heats it to millions, sometimes billions of degrees. It glows with a light more intense than 1,000,000,000,000 suns. But you don't see it as a flat disk. Because space-time is so warped near the black hole, the disk appears to bend upward and over the black hole, wrapping around it like a glowing halo. You see the top of the disk above the black hole. You see the bottom of the disk below it. And you see the far side of the disk as a thin, bright ring hugging the shadow's edge, all at the same time. It's one of the most beautiful and alien sights in the known universe. Closer still, and you encounter the photon sphere. This is the distance at which light itself can orbit the black hole. At 1.5 times the Schwarzschild radius, a photon traveling sideways can circle the black hole and come back to exactly where it started. If you hovered here and looked straight ahead, you would see the back of your own head. Your light has traveled all the way around the black hole and returned to your eyes. Inside the photon sphere, things become deeply strange. Light from the accretion disk wraps around the black hole multiple times, creating nested photon rings, each one a complete image of the disk seen from a different angle, each one thinner and closer to the shadow. In theory, there are infinitely many photon rings, each containing a complete picture of the universe viewed from a different epoch in time. This is not science fiction. This is what Einstein's equations predict. And the Event Horizon Telescope has already observed the outermost photon ring around the black hole in M87. Now let's talk about time. As you approach the event horizon, something happens that violates every intuition you have about reality. Time slows down, Not metaphorically, not poetically. Literally, your clock runs slower than a clock far away from the black hole. This is gravitational time dilation, predicted by Einstein in 1915 and confirmed by every experiment ever conducted. For you, the falling observer, everything feels normal. Your heart beats at its usual rate. Your watch ticks normally. But if someone far away could watch you through a telescope, they would see something profoundly disturbing. They would see you slow down. As you approach the event horizon, your movements become sluggish. Your light shifts to red, then deep red, then infrared. You appear to freeze, hovering at the very edge of the event horizon, growing dimmer and redder, but level equals strong, greater than never appearing to cross. From their perspective, you would remain there forever, a frozen ghost at the boundary of the black hole, slowly fading from view over years, decades, centuries. They would never see you fall in. But from your perspective, you cross the event horizon without even noticing. Chapter 3. Crossing the point of no return. Here's the strangest thing about the event horizon. There's nothing there. No wall, no barrier, no membrane, no sign that says point of no return. The event horizon is a mathematical boundary, not a physical one. It's simply the distance from the singularity at which the escape velocity equals the speed of light. Once you're inside, even if you had an engine capable of accelerating to 99.9% the speed of light, you could not escape. Because inside the event horizon, all directions point inward. Let me explain that, because it's the most mind-bending concept in all of physics. In normal space, you can move in any direction: up, down, left, right, forward, backward. Time moves in one direction, forward. You can't go backward in time. Inside a black hole, space-time is so warped that the roles of space and time literally swap. The singularity is not a place in space. It's a moment in time. A moment in your future that you cannot avoid, just as you cannot avoid tomorrow. Moving toward the singularity inside a black hole is as inevitable as moving forward in time. You can no more escape it than you can travel to yesterday. So what happens to your body? For a supermassive black hole like Sagittarius A star, the event horizon is large enough that tidal forces at the crossing point are actually gentle. You could cross the event horizon intact, alive and unaware. But for a stellar mass black hole, a black hole of 10 or 20 solar masses, the event horizon is tiny, just 30 to 60 kilometers across, and the tidal forces near it are catastrophic. The gravity pulling on your feet would be dramatically stronger than the gravity pulling on your head. This difference, this tidal gradient, would stretch you lengthwise and compress you widthwise. Physicists call this spaghettification. Your body would be stretched thinner and thinner, pulled like taffy, until you became a stream of individual atoms, a thread of matter falling toward the singularity. According to NASA's simulation, from the moment spaghettification begins to the moment you reach the singularity, 12.8 seconds. But even during those final seconds, what would you see? Looking outward, the universe would appear compressed into a shrinking circle of light above you. The entire observable universe, every galaxy, every star, every photon, squeezed into a brilliant ring that narrows as you fall. And below, you, ahead of you, in the direction you're falling, nothing. Absolute, perfect darkness. The singularity emits no light. It reflects no light. It is the darkest thing in existence. You would die, looking at the entire universe through a closing iris of light, with the end of physics rushing up from below. Chapter 4: Inside the Impossible. What happens at the singularity? The honest answer is, we don't know. General relativity predicts that at the singularity, matter is compressed to infinite density in zero volume. The curvature of space-time becomes infinite. Every equation we use to describe the universe produces an answer of infinity, which in physics usually means the theory has broken down. The singularity is where general relativity crashes. It's where our best theory of gravity admits that it doesn't have the answers. To truly understand what happens there, we would need a theory of quantum gravity, a unified framework that combines Einstein's gravity with quantum mechanics. And despite a century of effort by the greatest minds in physics, we don't have one. But what we do know is extraordinary. In 1974, Stephen Hawking made a discovery that stunned the physics world. He showed that black holes are not truly black. They glow, very faintly, imperceptibly, but they glow. Time equals 600 milliseconds, greater than at the event horizon. Quantum effects cause pairs of virtual particles to appear spontaneously. One particle falls in, the other escapes. Over unimaginable timescales, this process causes the black hole to lose mass, to evaporate. This is called Hawking radiation, and it means that black holes are not eternal. They die. A black hole the mass of our sun would take 10 to the power of 67 years to evaporate. That is a 1 followed by 67 zeros. Far, far longer than the current age of the universe, but not forever. And this creates one of the deepest problems in all of physics: the black hole information paradox. When something falls into a black hole, all information about what it was, its mass, its composition, its quantum state, seems to be lost behind the event horizon. But quantum mechanics says information can never be destroyed. If the black hole eventually evaporates completely through Hawking radiation, where did the information go? For 50 years, this paradox has driven some of the deepest thinking in theoretical physics. The latest research published in 2024 and 2025 suggests that the information is not lost. It's encoded in subtle correlations in the Hawking radiation itself, imprinted on the gravitational structure of spacetime outside the black hole. The information gets out, but in a form so scrambled, so encrypted, that reconstructing it would require measuring every single photon of Hawking radiation the black hole ever emitted. Think about that. A black hole doesn't just swallow information. It takes everything that falls in, every atom, every photon, every quantum state, and encrypts it across the entire history of its evaporation. Like a cosmic shredder that destroys the document but preserves every molecule of ink, scattered across trillions of years of faint radiation. Black holes are not just objects. They are the universe's ultimate information vaults. And in 2024, the Event Horizon Telescope gave us another revelation. They released the first polarized light image of Sagittarius A star's magnetic field, and what they found was startling. The magnetic field around our galaxy's supermassive black hole is remarkably organized, and its structure is nearly identical to the magnetic field around M87 star, a black hole over 1,000 times more massive, in a galaxy 55 million light-years away. Two black holes, vastly different in size, in completely different galaxies, separated by unimaginable distances, and they have the same magnetic architecture. This suggests that strong, ordered magnetic fields may be a universal feature of all black holes, a fundamental signature of how space-time organizes itself at the edge of oblivion. Chapter 5: What black holes tell us about reality. No human being will ever fall into a black hole. No instrument we can build will ever survive the event horizon. The interior of a black hole is, by the laws of physics, permanently hidden from us. And yet, in the last decade alone, we've done something extraordinary. We've photographed their shadows. We've mapped their magnetic fields. We've heard them collide from billions of light years away. We've caught flares erupting from the disk of Sagittarius A star using the James Webb Space Telescope. And we've simulated the complete visual experience of falling into one. Black holes have gone from theoretical curiosities to the most studied objects in modern astrophysics. And the reason is simple. Black holes are where our two greatest theories of physics collide. General relativity describes the large-scale structure of spacetime. Quantum mechanics describes the behavior of particles at the smallest scales. Both theories work perfectly in their own domain. But at the singularity of a black hole, both theories are needed simultaneously, and they contradict each other. Whoever resolves that contradiction, whoever finds the theory that unifies gravity and quantum mechanics, will have solved the deepest problem in all of physics. And the answer will almost certainly come from studying black holes. In October and November 2024, LIGO detected two remarkable black hole mergers. One involved a black hole spinning faster than almost any ever observed. The other, for the first time, showed a black hole spinning in the opposite direction of its orbit, something that shouldn't happen if it formed from a single collapsing star. The implication? Some black holes are second generation. They are the products of previous black hole mergers. A black hole that was itself born from the collision of two earlier black holes. Generations of black holes, merging and growing over billions of years, like a dark evolutionary tree, stretching back to the earliest moments of the universe. We are only just beginning to read the family tree of the cosmos, and perhaps that's the real lesson here. A black hole is the most extreme object in the universe, a place where time stops, where space curves in on itself, where matter is compressed to a point of infinite density, where the known laws of physics break down and something new, something we haven't discovered yet, takes over. And we found them. Not by going there, not by touching them, but by listening to ripples in space-time from billions of light years away. By photographing shadows cast on the glow of superheated gas. By writing equations on a chalkboard in 1915 and discovering, a century later, that every single prediction was correct. We are a species that evolved on a small rocky planet orbiting an ordinary star. And yet, from that tiny vantage point, we've managed to peer into the most extreme environments in the entire universe, places where time itself breaks down, and understand what we'd see if we were there. Don't take that for granted. That is not just science. That is the most extraordinary thing our species has ever done. If this video changed the way you think about black holes, do me a favor. Hit that like button. Share this with someone who loves the cosmos. And if you haven't already, subscribe to Final Frontier Space and ring that notification bell. We go deep into the places nobody shows you, and we do it every single week. I'll see you in the next one. Stop it, though.